Good evening, everyone. Thank you for joining us tonight for the second event in our RiverWatch Winter Speaker Series. For those of you who are new to the Illinois RiverWatch Network, RiverWatch is a citizen science organization that trains volunteers to monitor water quality in their own communities. The mission of RiverWatch is to safeguard the future of Illinois rivers and streams through stewardship, education, and sound science. Before we get started, I ask that you keep your microphone muted during the presentation to limit the distractions. If you have a question along the way, you can either put it in the chat box to be answered at the end of the talk, or you can save it and ask it aloud during the Q&A session. Now I would like to introduce today's speakers, Jen Brenner, Rachel Canopy, and Tegan Sandwich. Unfortunately, Tegan is unable to be here tonight, so Jen and Rachel will be presenting her part of the talk. And Rachel and Tegan are Joliet Junior College students who participated in the college's undergraduate research course in the fall semester. The research course allows the students to design and conduct their own research project. Their advisor, Professor John Griffiths, a longtime RiverWatch volunteer, helped them develop their research projects based on RiverWatch methods. Today, the students will be presenting the results from this class. And with that, I welcome Jen Brenner and Rachel Canopy.
All right. Good evening, everybody. Thank you for joining us today as we discuss how stream quality is determined by the presence of macroinvertebrates and chemical assessments. I'm Jen Brenner, and here with me is Rachel Canopy. Unfortunately, like Hannah said, Tegan couldn't be with us tonight, but her work will be presented nevertheless. Oh man. The French explorer Jacques Cousteau once said, we forget that the water cycle and the life cycle are one. Water quality in running water ecosystems is imperative to the health of the earth and its inhabitants. It's what we drink, it irrigates our crops, it acts as a filter for pollutants, and it's a habitat for flora and fauna. Benthic aquatic macroinvertebrates are small organisms that live entirely or partially in the water. They have no inner skeletal system, and they live in water and comprise of adult and larval insects, leeches, small crustacean, worms, and snails, and can be found attached to rocks, logs, sticks, vegetation, or even burrowed into the sand and sediment. We can collect samples of these and examine them in a very cost-effective way to determine the ecological health of a habitat. The presence and assortment of certain macroinvertebrates, which are also called taxa, can project the quality and health of our water system. Some macroinvertebrates flourish in polluted water, and we call those pollution tolerant, and an abundance of these organisms can indicate poor water quality. Other macroinvertebrates include the insect orders Ephemeroptera, Plecoptera, and Trichoptera, or EPT, and they need a higher quality and rapid flow of water to survive, and an abundance of these would indicate less pollution. This slide shows photos of different macroinvertebrates. The cute little guy on the left, who is my favorite, is the planaria, or the flatworm. The middle is the snail-cased caddisfly, and on the right is a non-biting midge. Running water systems are one of the most integral ecosystems in the world and have immense impact on the environmental health of the planet. So how can we determine water quality? Well, we can collect and compile data and take into consideration the factors I've listed here. Some of those are pollutants like litter in the water, industrial waste, pesticides, cleaners. There's erosion, organic waste, temperature elevation, channelization, pH levels, location, sample size, human activity, weather barriers, and chemical composition. Today, we'll be presenting several ideas conducive of affecting the quality of water in the stream systems. We'll be discussing physical barriers that reduce stream flow, seasonal variation, canopy cover, and artificial substrates. All these things are factors that could positively or negatively alter water quality. The first focus of the study is to observe how weather-related barriers or log jams have an effect on the velocity of running water systems and how seasonal weather conditions can play a role in how those weather barriers exist. So, do obstructions in the water affect the velocity? And does velocity affect the health of the running water in the ecosystem? The objective of this is to determine if seasonal weather-related barriers affect the velocity of the stream in either a negative or a positive way. My hypothesis is that the weather-induced water barrier will affect the water velocity. And my prediction was that the summer storm induced a log jam, creating a negative change in the water velocity and will show a significant decrease in the EPT taxa richness between the spring and summer sample, signifying more water pollution, and that the natural deterioration of the water barrier between the summer and fall sample positively change the water velocity and will show increased EPT taxa richness, indicating less water pollution. If you take a look at figure 1, this photo shows the log jam at Van Horn Woods in Plainfield, Illinois on September 4th, 2020. That was caused by a summer storm at the earlier time in the summer. This log jam caused the stream to have zero velocity on this date when the sample was taken. We extracted the data from Van Horn Woods East, located in Plainfield, Illinois, which is located south of US Route 30. The study site is a portion of Lily Cache Creek located on the south end of the park and can be accessed by a hiking trail through the woods. The sample site consisted of a portion of Lily Cache Creek, considered downstream, with roughly 55% canopy coverage, and surrounding vegetation consisted primarily of reed canary grass, giant ragweed, white oak, mulberry, and box elder. We chose 3 locations in the creek to collect samples. As the photo here in figure 2 show, we used a D-frame 500 micron dip net, which we placed in an upright position in the water with the net placed on the sediment on the bottom and the handle straight up out of the water. A person called a netter stood downstream and held the net so it rested on the bottom. And then another person called the kicker stood approximately a foot in front of the net and moved the sediment around in front of the net with a shuffling motion to a depth of 3 inches for 3 minutes. This disturbed the sediment and kicked it into the net. After 3 minutes, the netter scooped the net out of the water and transferred the contents of the net into a 5-gallon bucket by inverting the net and rinsing it with a wash bottle. Creek water was added to the bucket to preserve the sample during transportation. The net was then examined for any organisms that may have been missed. This procedure was done at each of the 3 locations in the section of the creek that were chosen. The samplings were done on June 15th, 2020, September 4th, 2020, and October 20th, 2020. Measurements for velocity and air temperature were noted on each sample day. As you can see here in table 1, the spring sample was collected from a riffle and snag on June 15, 2020, when the air temperature was 81 degrees Fahrenheit, 27.2 degrees Celsius, and the water temperature was 71 degrees Fahrenheit, 21.7 degrees Celsius, and the stream was flowing at a typical velocity of 0.46 meters per second. Then we see the summer sample was taken on September 4th, 2020, when the air temperature was 71 degrees Fahrenheit or 21.7 degrees Celsius, and the water temperature was 64 degrees Fahrenheit or 17.8 degrees Celsius. We used the slow riffle and the fast riffle from the previous spring sample for this collection, even though there was no riffles at the time due to the earlier storm that created the log jam, and as a result, the velocity was 0. This third sample was taken on October 20th, 2020, and the air temperature that day was 44 degrees Fahrenheit or 6.7 degrees Celsius, and the water temperature was 47 degrees Fahrenheit or 8.3 degrees Celsius. This sample was collected by scraping 3 snags for 15 minutes total. Sedimentation made it difficult to sample snags, so that to obtain an adequate sample, additional snags had to be scraped. As figure 3 shows here, a portion of the sample is transferred to one of 2 subsampling trays for examination. Water was placed in the tray along with a portion of the organism collected. All excess material like cobble, gravel, leaves, sticks, and other surfaces were carefully examined, and any organism found were removed and placed in a different 12-quadrant subsampling pan filled partially with club soda. This procedure was done until the entire sample had been examined and all macroinvertebrates had been found. All the excess and the leaf litter and sticks and rocks, they were all returned to the creek. Once all the macroinvertebrates had been found, a sample of a minimum of 100 organisms was chosen using randomly generated numbers from 1 through 12, where each number corresponded with 1 quadrant of the subsampling tray. The chosen specimens were placed in a jar containing 91% isopropyl alcohol, labeled with the date and the location of the sample, and brought to the lab to be examined, counted, classified under a dissecting microscope. Here, figure 4 and 5 show the samples being viewed under the microscope and a few sample dishes that we worked with in the lab. The examining and counting process was done several times to ensure accuracy, and results were recorded in accordance with the Illinois RiverWatch protocol procedure. These equations here were used to determine the MBI, or the macroinvertebrate biotic index, and the SDI, which is the Shannon diversity index for each sample. EPT and non-EPT individuals and pollution-tolerant, intolerant organisms were calculated. According to Illinois RiverWatch protocol, taxon with a tolerance index value, or a TI, of less than or equal to 5.5 would be classified as pollution intolerant, while taxon with a TI of greater than 5.5 would be classified as pollutant tolerant. Analysis using chi-square, a statistical test comparing the difference between actual counts to expected counts, was used for EPT, non-EPT, and pollution tolerant, intolerant data. So as we look at the results here in table 2, we see the total number of organisms subsampled varied slightly with the summer date. Let's see, right pointer. Producing the largest sample here at 147, and the fall sample producing the smallest sample at 98. The taxa richness, or the number of diverse species of a sample, of 18, and the EPT richness of 6 here, was the highest in late spring sample, which was the warmest air temperature and water temperature of the samples, and the stream was not hindered with the log jam at this point, and the positive velocity was 0.46 meters per second. The late summer sample, showing 0 velocity, had slightly more taxa at 14 than the early fall, showing 12, and had positive velocity of 1.145 meters per second, but both had the same EPT taxa numbers of 3 here. The EPT taxa richness of both the summer and fall sample when the log jam was present was 50% less than the spring sample when there was no log jam. The ratio of the EPT, non-EPT organisms showed significant differences between all 3 samples compared simultaneously between late spring, where they were positive velocity, and late summer, where there was 0 velocity, and between late spring with positive velocity and early fall with positive velocity. The spring sample was taken prior to the log jam, disturbing the velocity in the stream, and quality declined slightly from the late spring positive velocity sample with an MBI of 5.14, which is considered fair quality, to late summer of 0 velocity, and the MBI is 5.44, which is still considered fair. And then it was compared to the early fall sample with a positive velocity and an MBI of 5.83, which is poor quality. The fall quality occurred after the logjam that had blocked the stream flow naturally began to break down in the spots and allowed the water to flow again. Diversity, as indicated by SDI values, was lowest in the late summer, right there, at 1.8, compared to late spring at 2.3 and late fall at 2.03, both with positive stream flow velocities. The ratio of EPT, non-EPT organisms did not vary significantly between the late spring with positive velocity and early fall also with positive velocity, with a p-value of equal to 0.21. Whereas at this point, the logjam was in place for an extended period of time and the seasonal temperature were cooler. The ratio of pollution tolerant showed a significant difference between the spring sample and the summer sample with the p-value of equal to 0.01, but varied the most between the summer sample and fall sample with a p-value of 0.006, showing significant differences. Spring by far the greatest EPT individual in the sample with 58.6 of the sample, with hydrocyclic caddisflies highly dominant and clinging mayflies a distant second. Late summer with 0 velocity and fall with positive velocity had only 7.5% and 12.2% respectively for EPT individuals in the sample. The dominant taxa in summer were narrow-winged damselflies and midges. In the fall, midges followed by the narrow-winged damselfly and operculate snails, all that are non-EPT taxa, were the dominant species. Comparisons between season velocity samples were significantly different for pollution tolerant individuals sampled for spring/summer and summer/fall. Spring/fall results for pollution tolerant had no significant difference. Spring to summer to fall had a decreasing trend in percentage of pollution intolerant individuals collected, with 75% to 60.5% to 42.9% respectively. In conclusion, I believe that my hypothesis was predicted and prediction was supported. The logjam initially had a definite effect on the velocity of the stream, thus decreasing the EPT taxa richness. As the logjam started to deteriorate, the water velocity increased and the number of EPT organisms went up slightly. Late spring with positive velocity displayed the highest stream quality as determined by MBI and presence of EPT taxa in individuals, as well as other pollution intolerant taxa and specimens. 0 velocity was found to have the lowest diversity in EPT. Diversity improved after stream flow broke through the logjam in the fall sample. However, quality was determined to be less. The logjam blocking the stream flow may have affected quality and EPT. However, the seasonal differences appear to have the greatest impact, reflecting change due to life cycle and other environmental factors like water temperature. Various studies suggest contradictory results. A 2015 study by Ryder and Associates stated that although decreased water velocity showed no significant difference in the diversity and richness, it did cause a change in the community composition. Contradicting that is a 2011 study done by Mueller and Associates stating that the presence of a logjam caused a low flow site and significantly alters not only the community composition, but also the diversity of the stream. Results may vary for numerous reasons. Not only the season change and the varying water air temperature, but also the life cycle of the organism should be taken into account. The shape of the stream, volume of water, gradient of the slope, and friction along the edges can also have an impact on the velocity as well. Future experiments would also benefit from having a consistent time span between each sample taken. And in this study, the time span between the late spring and late summer samples was 81 days, while the time frame between the late summer and early fall dates was only 46 days. Collecting a bigger sample overall and taking several samples spaced evenly apart in each season could also influence the results. Overall, more studies are necessary for more accurate results to conclude if log jams and other obstructions in running water play a part in determining water quality.
Hello, everyone. My name is Rachel Canopy, and I will be leading you through my research, which focused on the impact of environmental factors, specifically canopy cover and seasonality, on stream quality determinants as they influence macroinvertebrate communities. I want to begin by quickly defining some terms. The first is canopy cover. I'm referring to the overcast caused by trees that are positioned along a stream's edge, which is formally called the riparian zone. The second definition is seasonality, which is the occurrence of periods within a year that induce characteristic changes of biotic factors, such as population sizes, and abiotic factors, such as temperature and pressure. This research was driven by the hypothesis that seasonality and canopy cover generate variations in stream quality determinants. The prediction was that the percentage of canopy cover would influence the kind of macroinvertebrates found in the samples, producing significant differences in EPT, pollution tolerant and pollution intolerant ratios, MBI and SDI ratings from the spring season to the fall season. As an overview, I will first describe the methodology of this research, then briefly set out the data that was analyzed, and thirdly discuss the results in light of the hypothesis and prediction and what sort of conclusions were gathered from them. At the end of this presentation, you will understand the purpose, discoveries, and implications of this research, as well as gain a little bit of insight into the field of stream ecology. The research took place on Lily Cache Creek at two sites. The first was the Van Horn Woods East location in Plainfield, which was accessed by a trail. The canopy cover at this site was determined to be 50% based on subjective measurements. The other site was located behind the Four Seasons baseball field in Plainfield, Illinois, and was classified as an open canopy site, having 0% canopy cover. So to reiterate, canopy cover is defined as the overcast caused by riparian trees. As you can see, the trees in the left photo at the Van Horn Woods site create shadows on the surface of the water, while in the right photo at the Four Seasons location, there are no shadows on the water because of the absence of canopy cover. These photos were taken in the spring season in the month of June, but other photos were taken in September and October to observe the visual aspects of seasonality at the sites. The methodology consisted of taking samples from each site at different times in the year. The spring samples were collected prior to this research in June. The summer samples were taken in September, and the fall samples were taken in October. At the time of each sample collection, physical features were measured at each site, including algae and water temperature. As described in the Illinois RiverWatch Stream Monitoring Manual, the kick technique was utilized to collect the samples of macroinvertebrates. At each site, the shuffle dance, as it's called, was applied to a riffle, angling the D-frame net once upstream and once downstream. Approximately 3 snags or log pieces that are partly submerged in the water, as shown in figure 10, were scraped with the D-frame net as well. The macroinvertebrates were subsampled to 100 individuals minimum and identified in the lab under dissecting microscopes. The samples were evaluated using the MBI and SDI, or macroinvertebrate biotic index, and Shannon Diversity Index, and the number of EPT and non-EPT taxa and number of pollution tolerant and pollution intolerant taxa were calculated and compared statistically using chi-square analysis. The equations for these were explained earlier in Jennifer's research. And in figure 11, you see a broad-winged damselfly observed under a microscope. A portion of the results is shown here in table 3, revealing the Shannon diversity values of the samples, MBI scores, and the stream quality ratings based on the MBI. Diversity is considered to be good if the SDI values or Shannon Diversity Index values is high. As you can see right here, this is a high value at the Van Horn forested site. And right here, we have a high value at the Four Seasons site, both in the spring. And when I refer to diversity, I'm indicating both the number of macroinvertebrate taxa that appeared in the samples, as well as their relative distribution. In this table, the Four Seasons open canopy site had higher diversities than the Van Horn forested site. The MBI, which measures water quality in the second column here, it works oppositely than the Shannon Diversity Index in that the low values indicate better water quality and vice versa. Regarding the seasonal trend in the MBI, the forested site experienced a decline in water quality as the MBI values increased. And at the open canopy site, it experienced an improvement in water quality as we moved from spring to summer to fall. Chi-square analysis compares actual amounts to what is predicted. And if the p-value generated exceeds 0.05, then the relational difference is insignificant. Here, the results show significant differences in the seasonal comparisons at the forested site in this top column. All the pollution tolerant, pollution intolerant individual values were significantly different for each seasonal comparison at the forested site, right here. The only invariability was observed for the EPT versus non-EPT between the summer and fall sample comparisons. So these samples looked somewhat close as to the kinds of individuals that were in them. In the second column, for the open canopy site, the significant differences were limited to pollution tolerant, pollution intolerant, comparing spring to fall samples, right here. All the other p-values showed that there was no significant difference in the organismal numbers that were compared. All of these exceeded 0.05. In this third column, comparing both sites, the spring season was highly variable, right here. In contrast, the summer season had no significant differences between the samples. And finally, the fall season only had a significant difference in pollution tolerant and pollution intolerant individuals within the samples between the sites right here. The hypothesis that seasonality and canopy cover generate variations in stream quality determinants, and the prediction that the percentage of canopy cover would influence the kind of macroinvertebrates found in the samples, producing significant differences in EPT, pollution tolerant and pollution intolerant ratios, MBI and SDI ratings from the spring season to the fall season were supported. With that said, let's look at how the results lead to this conclusion. Firstly, the open canopy site maintained greater diversity than the forested site, perhaps due to better quality food resources. Going back to table 3, the open canopy site had greater diversity than the forested site. As you can see, these values overall were greater than these values up here. In a study looking at canopy cover, substrates, and gradients on the structuring of macroinvertebrate communities in Oregon streams, Hawkins, Murphy, and Anderson found that sites with more canopy cover provided food resources that were poorer in quality than those provided at open canopy sites. The reasoning was that canopy cover limited the amount of in-stream nutrients like algae and periphyton for the macroinvertebrates to consume. This coincides with the algae measurements that were taken at both sites. There was more algae found at the open canopy site. Canopy cover provides outstream food resources, while stream algae provides in-stream food resources that tend to be better at accommodating for various macroinvertebrate populations. Now, there was a drop in the diversity of the forested and the open canopy sites. And this may also be correlated to food resources. I want to note that Kelly, Bothwell, and Schindler observed that excess light exposure can hinder algal growth. This may explain why the SDI values at the open canopy site decreased more than the forested site, because this value is less than this value right here. And the reason why this happened, perhaps, is because the algae was not as effective in supporting a diverse community in the summer season because of the nutrients that were perhaps damaged. And especially in the summer season when light intensity is at its peak. So that's probably what we're seeing. So to summarize, the open canopy had greater diversity than the forested site, and this was likely due to higher quality food resources. Secondly, seasonal variations in EPT, non-EPT, and pollution tolerant and pollution intolerant were observed at both sites, but to a lesser degree at the open canopy site. As you can see in this first section, there were significant differences between EPT and non-EPT taxa in the spring to summer and spring to fall season comparisons right here. In the right column, all the pollution tolerant and pollution intolerant comparisons were significant. The numbers of macroinvertebrates in the samples were highly variable from season to season at the forested site. This coincides with Helms, Schoonover, and Felmanella, who, after studying the impacts of seasonal variability of land use on macroinvertebrate communities in Georgia streams, found that seasonal differences in macroinvertebrate communities increased with the percentage of canopy cover, and there was much more seasonality occurring at the Van Horn forested site. In the second section here, the open canopy site, there were no significant differences between EPT and non-EPT individuals in the samples. The only significant difference in the pollution tolerant and pollution intolerant individuals was in the spring and fall comparison right here. Overall, you can see that the forested site had much more variability with the sampled macroinvertebrates from season to season than the open canopy site. Though both did demonstrate seasonality, this one, the forested site, demonstrated it more obviously. Thirdly, regarding seasonality, the forested site increased in pollution tolerant individuals. And you saw in that other table that the MBI ratings declined. The MBI values increased at the forested site from spring to summer to fall. In accordance, the MBI quality ratings declined from spring to summer to fall. The seasonal increase in pollution tolerant individuals at the forested site was detected by the MBI, showing the declining tendency. This progression contrasts the work of aforementioned Helms, Schoonover, and Felmanella. They discovered that stream quality improved with the amount of deciduous riparian vegetation. The tendency of declining water quality at the Van Horn Woods site contrasted their results. Fourthly, the greatest seasonal differences were observed in the spring samples. Both sites yielded similar individuals in summer and fall. In the third portion of this table, table 4, where both sites were compared at corresponding seasons, the spring season generated great seasonal variability between the samples. So the samples were more unique to their environment. So the EPT, non-EPT ratios and the pollution tolerant, pollution intolerant ratios were significantly different from one another. As seasons progressed into the summer and fall, the samples began to resemble each other, and therefore no significant differences were observed. And in the same way, in the fall season, the only significant difference was found between the pollution tolerant and pollution intolerant individuals. And you can see that also right here in the Four Seasons and in the Van Horn, these two were both significant. And between the two sites, they were significant. This is where they started to diverge a little, where the forested site started to gain pollution tolerant individuals, while the open canopy Four Seasons site began to lose pollution tolerant individuals. So that's why we see this discrepancy right here. But with EPT, these two looked mostly identical. Supported by the information above, seasonality is reflected in stream quality determination, and especially at forested streams. From this research, seasonal variations were strongly detected where canopy cover was present, pointing to the influential role environmental factors play on macroinvertebrate communities and the monitoring of stream quality. As a final statement, the interactions of biotic and abiotic factors should continue to be explored and understood in order to constructively respond to and repair polluted ecosystems. Thank you very much. At the beginning of this presentation, it was conveyed that Tegan Sandvik was not able to deliver her research this evening. I will be speaking on her behalf. Tegan's research compared the effectiveness and longevity of two kinds of samplers, the rock basket and the Hester Dendy. Sampling methods are distinguished as either being active or passive. The kick-neck technique used in Jen's and my research was an active sampling method. Rock baskets and Hester Dendy samplers, however, are considered passive sampling methods because they require a longer duration, taking advantage of stream drift, which is the initial step in the colonization of macroinvertebrates. The hypothesis was that different artificial samplers will result in differences in macroinvertebrate colonization and therefore affect stream quality determination. Tegan's prediction was that if rock baskets and Hester Dendy samplers were set adjacent to one another, then differences in macroinvertebrate colonization will result, affecting determination of stream quality at 3-week and 6-week colonization times. The sample site was at Lily Cache Creek, just beyond the Four Seasons baseball field in Plainfield, Illinois. On September 14th, 2020, within approximately 15.2 meters of the upstream study area and about 1 meter from the north bank, a pair of rock baskets and a pair of Hester Dendy samplers were placed adjacent to one another and secured with stakes in a spot that had a high velocity just ahead of a riffle. After 3 weeks, on October 5th, 2020, a rock basket and a Hester Dendy were retrieved from the site. After an additional 3 weeks, on October 30th, 2020, the second rock basket and Hester Dendy were retrieved from the site. Figures 12 and 13 on the right depict the before and after conditions of the 3-week period. When retrieving the samples, 2 kick nets were held close to the downstream side of the artificial substrates to catch any disturbed substrate contents. Each sample, the devices, the stakes, and the aforementioned kick net contents were placed in a 19-liter bucket filled 1/4 full of stream water. The structures were disassembled, every piece, removing plant life and macroinvertebrates colonized on the substrates. The samples were whole samples, meaning every macroinvertebrate qualified by RiverWatch was counted. Once the samples were collected, they were taken to the lab to be inspected under dissecting microscopes, and the data was analyzed and compared statistically. Stream quality was determined using the MBI, total taxa or abundance, EPT and non-EPT taxa, and pollution tolerant, pollution intolerant taxa were analyzed. The Shannon Diversity Index was used to determine the diversities of the samples. The results revealed that each sampler contained a minimum of 100 macroinvertebrates. Additionally, there was no significant difference of colonization due to the type of sampler nor longevity in the stream. The sampler with the greatest abundance of macroinvertebrates was the 6-week Hester Dendy, but the 6-week rock basket had offered the greatest diversity. The 3-week Hester Dendy had the greatest abundance of organisms, but the 6-week rock basket offered the best taxa richness and diversity. Although there were some differences in the EPT and non-EPT individuals, according to the RiverWatch stream quality rating, between all of the 3- and 6-week samplers, the stream quality was determined to be the same, fair with some pollution. Significant differences were found for EPT compared to non-EPT for comparisons of 3- and 6-week colonization for the rock baskets, and for a 3-week rock basket Hester Dendy, and the 3-week rock basket and the 6-week Hester Dendy. There were no differences observed between the 3- and 6-week Hester Dendy devices, and between the 3-week Hester Dendy and the 6-week rock basket, and between the 6-week Hester Dendy and the 6-week rock basket. The comparisons of pollution intolerant individuals sampled were significantly different between 3- and 6-week rock basket samples, and all other sample comparisons of the rock baskets and the Hester Dendys. However, there was no difference between the 3-week and the 6-week Hester Dendy samplers. Shannon diversity indices were all, index values were all similar for the 6-week rock basket and 3-week Hester Dendy samples, but were slightly lower for the 6-week Hester Dendy sample, and the lowest was in the 3-week rock basket sample. The hypothesis and prediction were partially supported in this research. Differences between the rock basket and Hester Dendy were greatest at comparing the 3-week samples, but less obvious at comparing the 6-week samples. Both resulted in a stream quality designation of fair and with no significant differences between EPT and non-EPT. The prediction was supported in that different macroinvertebrates colonized in different proportions, and significant differences in pollution-tolerant and intolerant individuals were observed. Length of colonization was not found to affect stream quality. Also, the method of sampling did not affect macroinvertebrate colonization. The rock basket sampler offered a more consistent sample between the 3- and 6-week period of time in comparison to the Hester Dendy method. This could be due to the more intricate surface and texture of the rock basket that enabled easier colonization for drifting macroinvertebrates. The drift that brought some of the macroinvertebrates in very well could have taken them out as well. Although a study done in New Zealand stated that drift does not seem to directly affect the colonization rates, the same study found that the peak of colonization occurred in the early stages. Upon retrieving the rock baskets, the pressure of the water passing through the rocks could have washed away some of the macroinvertebrates. Additionally, in between the 3- and 6-week retrieval times, there was a rise and fall of the stream depth, which could have impacted the total sample by slowing or increasing the flow of macroinvertebrates in and out of the samplers. In conclusion, both of the samplers worked rather well. Neither of the devices seemed to be affected by the length of the colonization period. The EPT to non-EPT, the pollution-tolerant to pollution-intolerant individuals, and the Shannon Diversity Index results offered the most variation in the rock basket device in comparison to the Hester Dendy. The stream quality rating was unaffected by either method. This presentation was supported by the following references.
All right, thank you guys for the presentation. It was very good. We're now going to open it up to questions. Anybody is welcome to unmute yourself and ask the question aloud or put it in the chat box and I'll read it to them.
Do you want us to exit out of this?
I didn't get to read my acknowledgements.
Oh, go ahead.
I couldn't get my thing off mute. So sorry. We would like to convey gratitude to Joliet Junior College for providing a science department that incorporates hands-on learning. A very special thanks to biology professor Dr. John Griffiths for the opportunity to work on this research project. His careful guidance, vast knowledge, immense patience, and the sense of humor made the experience educational and enjoyable. A great thanks to our team, Rachel Cannon, Tegan Sandvik, and myself for assisting in the data collection and research on this project. We'd also like to thank the Joliet Junior College Laboratory Coordinator, Christine Noel, and Laboratory Assistant, Kim Crow, for organizing the equipment and supplies needed to complete this research. We would also like to thank you for taking the time and giving us an opportunity to share this research today. Any questions?
Okay, there is one in the chat box from Danielle. She asks, if you were going to continue these studies, what would each of you do to improve or expand on your work?
Ooh, may I answer that first?
Yeah.
So for mine, I would actually dive a little deeper into the functional feeding groups of each of the macroinvertebrates, because food resources was one of the main components in the discussion, because the trees offer a different kind of food resources versus like an open canopy site that was mainly dependent on like algae and plants that are within the stream. And so I would actually look at how the macroinvertebrates feed. So like there's scrapers and grazers, and they feed on just different substrates. So it would be interesting to look not only at canopy cover and the open canopy, but also look a little deeper into how the macroinvertebrates feed on what is coming from the trees and the vegetation on the side. So that was a good question.
For me, I would just really like to just take more samples, and like I said in my part of the presentation, like take more samples like in a distinct amount of time apart, and just like really correlate it with the weather conditions, and if the logjam is had an effect on the flow and the velocity. So like just getting more into it with more samples and more words are hard. Yeah, so there you go. Sorry.
You're good. Does anybody else have any questions? This is from Brittany. Rachel, when you talked about your study having an opposite outcome from previous studies, do you think this was due to variations in weather, temperature, or some other variable?
Yes and no. Each research, like when I was researching, it seemed that a lot of different research gave different answers to the main influencer of it all. It could be that temperature was involved somehow, or maybe the substrate, like the sediment. It could have been, it could have, there were other factors that couldn't quite be isolated. So I could only really infer. And so, yeah.
Did you guys do anything like tracking what the weather was or like anything like that to compare the seasonality, or did you just look at temperatures?
I mainly looked at temperature, and I also looked at algae, because seasonality can affect growth of algae, and because algae was such a major food resource that could come up in it, I looked at that. Also, velocity is one that can be affected seasonally. You can also look at the depth of the water usually fluctuates. Of course, temperature is probably one of the main components because it gets colder and warmer. Oh, and another thing too with that is life cycles. Most actually of the macroinvertebrates are insects, and so they either have a complete or incomplete metamorphosis, like a life history. And so sometimes when you sample at a certain time in the year, you'll only get the prevalence of that one population that at that time is present in the stream. But in a month to later, it's gone. And we saw that with the, I believe it was the hydrocycid caddisflies. They appeared in the spring, like it was just booming, but they were totally absent in the summer and fall samples. So life cycles definitely comes into play with seasonality.
If you guys were to continue and do winter samples, do you have any predictions for what those would look like? If not, that's okay. I know that's not something that you guys specifically were looking at.
With mine, there was one study that actually had the canopy cover improve again into the later winter. And so I'm curious, since the results of my research really focused on the decline of water quality at the forested site, it would be interesting to continue the sampling into the winter so that you can maybe find that comparison between this other study to see if maybe the canopy cover will actually improve as you get further and further into the winter. So I would, but it's cold.
Yeah. I kind of like to see it too, just because with streams and creeks and the ice in the winter, how that would affect the velocity, or to see what the different samplings would bring.
Okay, are there any other questions from anyone?
I would like to, this is John Griffiths, who was, as the advisor. And I see this thing in the chat from Phil about Hesterdendes and rock baskets. And since Tegan isn't here, I thought maybe I'd answer that.
Oh, I missed that. Go ahead.
The Hesterdendes were very consistent at 3 weeks and 6 weeks. The rock basket's much more variable. By 6 weeks, the two were not variable in regard to EPT, non-EPT, pollution tolerance, pollution intolerant individuals, and MBI, but they did collect different proportions of macroinvertebrates. So taxa were different, but the outcome when you're looking at those particular factors were not different. Now, just real quick, one of the take home that I got out of this is, you really need at least the 6 weeks for colonization with these, particularly for the rock baskets. However, if you were really short on time, a 3-week sample using the Hesterdendes would give you pretty much a similar result as the 6 weeks. And, generally speaking, they say about 6 to 8 weeks for these artificial samplers to get a good sample. So there's a lot of literature out there, a lot of debate on this. So hopefully that sort of answered that question.
Do you know which type of sampler offers more surface area?
We did calculate surface area, and gosh, I can't offhand remember exactly what that was. It was a really rough estimate because of the bank rocks we were using, and I just did the best I could. So yeah, one of the things you look at is you look at per meter squared a lot of times with surface area. But if you want an accurate determination, you have to do stuff like take aluminum foil and wrap it around each rock and then lay it out and then measure it. And
yeah,
honestly, we weren't willing to do that. So. But different surfaces, we've done study on different surfaces, and more roughened surfaces definitely are better at collecting macroinvertebrates than smoother surfaces.
Yeah, and for those that don't know, the picture of the Hesterdendi only really showed the brick on top, but underneath the brick are little, what are they made out of?
Masonite plates.
Yeah, so they're like square plates that are pretty thin and they're like stacked together on a screw. So that's what the Hesterdendis look like.
Yeah.
Looks like a small building.
Yeah. And I wanted to thank my students too, because they did a great job. So I really appreciate that and filling in for Tegan not being here. So thank you.
Mm-hmm. Yeah, and it's just my question. Thanks you guys for all this cool information. I've been doing research with Hesterdendis myself, and that is something that I've been thinking a lot about. So I guess if there's maybe more time offline or something, I'd love to follow up with you guys and see exactly what you were using, because I am also looking for different ways to sample macroinvertebrates, especially going into the winter months, because as you mentioned, it's pretty uncomfortable and not exactly a whole lot of yield. So yeah. Very interested in, and this is a great talk. It's very interesting for me.
Yeah, and I've done I like Hesterdendis personally, although they're heavy to put in and out with the bricks and stuff, and rock baskets. So we've done quite a bit with them, and you know, it's always interesting to me. So I'd be willing to talk to you about that anytime.
Okay, if does anybody else have any questions? All right, well, thank you, both of you, for presenting, and Tegan, even though she wasn't able to be here. And thank you, John, for helping to answer questions.
Yeah, and for those of you who are left, we do have a few more things coming up for the speaker series in the next several months. So actually in about a week and a half, I guess, on February 11th, we will have Sarah Douglas from the Illinois Natural History Survey speaking with us about freshwater mussels. And then on February 17th, we have Katie Whitlow talking about underwater adventures in Illinois. So who knew that you could scuba dive in Illinois? So we'll get to learn more about that.
Thank you. Thank you very much.
Yes, thank
you everybody for coming.